Hi guys. Last time we discussed about the dynamics of continuum media, and we'll start over by reviewing the dynamics of a string. Then we consider the beam equation. We make some little references to the effect of dispersion, and then we will pass to discuss the vibrating shell. Okay. Last time we considered an infinite spring, an infinite string, right? Subjected to a tension T. We assume that the tension is constant and it is independent on the actual deformation of the string. So we have two angles, theta and theta plus d theta over ds, where ds is the abscissa which spans the length of the string. The string has mass density rho, and we call v of st the displacement field of the string. Is a function of two variables, the abscissa, which spans the length of the string, and the time t. So we write the equilibrium equation of this infinitely little element of string of length ds. If there is an acceleration, as you know, everyone knows that. So the inertial forces are rho ds, which is the mass, times the double derivative of v with respect to time. We denote with the double derivative with the Newton notation, which is double. Okay. Which is actually so writing the equilibrium equation, we have t times minus t times sine of theta. So we take the projection on the vertical direction plus t sine theta and it is equal to if it is in the opposite direction. If the v is positive, then the double derivative, the inertial forces are negative. So they are equal to rho ds dt squared. Now we assume that the length of the string is equal to its projection on the x-axis. So the ds is approximately dx. If you consider a guitar and the string of a guitar, you won't see the string of the guitar vibrating. It's likely it remains still. It doesn't move because the displacement is very, very little. So this approximation is a good approximation when we are talking about low displacements. Right. So the derivative with respect to ds becomes a derivative with respect to x. So, and theta is very little. So the other approximation is that we assume sine of theta approximately equals to the tangent of theta, which is approximately equal to, dv over dx. Okay. So we have minus t by simplifying this expression, we have so the equilibrium equation, the indefinite equilibrium equation of a string is T times dividing by T, we have where C0 is the ratio T over rho. And it's called phase velocity. This equation is very famous because it represents not only the dynamics of a string, but it is representative of a wide class of phenomena, and not secondarily, it represents it is called the wave equation. Because this equation represents all the simplest wave propagation phenomenon. You have to keep in mind this equation. So we apply the concept of wave equation to the string, but it's valid for other structural elements. Let us consider another structural element, which is the bar. We have a bar, an infinite bar, like a rod. And we study the axial displacement, which is represented by a function u of xt, where x is the abscissa that spans the length of the rod. So let us consider the equilibrium equation. We have the element dx with mass rho dx. The inertial forces are rho double derivative dx, and then we have the result of the axial force N. So the equilibrium can be written as but dn can be approximated by dn over dx times dx. But n, the constitutive equation is EA, the strain, the axial strain, du over dx. So if we plug this term inside this one, we have the dn is equal to EA. If EA is constant, it's equal to dA, the double derivative of u over dx squared. So substituting inside, we have EA du dx squared is equal to rho du dt squared. the equation becomes we divide both terms by EA, the axial rigidity. We have where C0 is actually EA over rho. The same equation. Two phenomena, two structure elements, the string, the vibrating string, and the bar. The equation is the same. We consider another structural element that is very familiar in the field of geotechnics. We consider a soil, a layer of soil depth H. Okay? And we consider the equilibrium equation of a small element subjected to shear stresses. The element has mass density rho, and we consider that the displacement field is the horizontal displacement, because it's like shaking horizontally, like a cake, and it is u of zeta, which is the depth t. So we write the equilibrium equation. We have the inertial forces are u rho dx dy, because it's the areal element, times the double derivative of u over dt squared, and it is equal to the shear forces. These two forces. So it's minus tau dx plus tau plus d tau over d zeta dx. D zeta, okay. Sorry, it's tau. This is the element. So this is dx and dy. So we want to have the total forces. This is a tension. So we have to multiply by its length. This is tau dx. And this one is tau plus tau dx. Plus tau over dy dx. Sorry. What does it mean? That if we have the element, here we have a certain tau, but the tau up here is different and could be tau plus tau d tau over dy. And y is the vertical. So now we can call it y, because it is the xy plane. Okay. Right. But tau is g, the shear modulus, times gamma, which is the shear strain. But the shear strain is g du over d x dy because we are looking for the variation of the displacement in the vertical direction, which is y. So it's the shear strain gamma is du over dy. Okay. If we divide both terms by dx dy and we plug this inside the equation, we have rho d squared u over dt squared is equal to g d squared u over dy squared. If we divide by rho and we call C0 as the square root of g over rho, we will have the wave equation, which is the same as this one. So, in conclusion, we considered three structural elements: a string, a bar, and a layer of soil. The wave equation is the same and can be written as d squared u over dx squared is equal to the only thing that changes is the value of the phase velocity, which is t over rho in one case, or EA over rho, or G over rho. As we see, the phase velocity is always expressed as a ratio between the elasticity and then the inertia. The velocity of a wave propagating inside a medium is always the ratio between how the medium is rigid and how is the density of the medium. So it is always the ratio between elasticity and inertia. You have to remember this, because when we deal with other more complicated phenomena, like the propagation of electromagnetic waves, we will find the expression of the phase velocity. But we will interpret this this expression in the light of in the light of mechanics. So we'll interpret this equation as the ratio between elasticity and inertia. In fact, many physicists talked about, as you know, about electromagnetic waves. You know that they propagate in the void. But many physicists in the early 20th century could not believe that a wave could propagate in the void, and they assumed that the void was filled with a sort of material which we do not know, which is called ether. And we will have the elasticity and inertia of a material we do not know, and later we will discover that there is no ether, this is just void, but we need mechanics to interpret more complicated phenomena. So understanding the wave equation in the structural elements in mechanics is important to understand more complicated phenomena. An important remark has to do that the phase velocity is constant and it is independent on the frequency of the wave it is propagating. The wave equation is representative of a so-called non-dispersive media. It's a non-dispersive medium. This is fundamental. The wave equation is representative of a non-dispersive medium. Then now we will go back to the string equation and we will try to solve the equation. We assume that the general solution of the homogeneous equation without no forcing term has the following expression. It is a big U of x times a function of t. We call it the method of separation of variables. If we substitute this expression inside the wave equation, we will have, now we will make the short notation of derivative. So I won't write the Leibniz notation, no Leibniz notation. We will have the simplest form. You see, du over dx squared is just this one. Okay, so u times t is equal to we divide, it's just substituting this inside this. We derive by x double derivative. This is a constant because it does not depend on x. Then we derive over t, but it is a constant because it does not depend on t. So we, you can see it. Yes, I hope so. So we have this one. If we divide both terms by t and u, we have this expression. U what does it mean? The first term on the left side of the equation is depends just on x. It's just on x. And the right term depends on t. So how a term dependent on x can be equal to a term which just depends on t? The only condition where the two terms are equal is that they are both equal to a constant. And we call this constant minus gamma squared. Minus gamma squared. And I'll show you why. The great thing about the method of separation of variables that we had a partial differential equation, a second order partial differential equation, and now we will have two second order ordinary differential equations. Okay. It's equal to And the other equation is T everybody knows which are the solution of these ordinary differential equations. This is the differential equation of we encounter this equation in the pendulum. We encounter it everywhere. The solution is the sine and cosine, it's the harmonic. So u of x is a cosine of gamma x plus b sine of gamma x. And t is c cosine of, we just call it omega squared. So we call omega squared c0 squared gamma squared. Cosine of omega t plus b sine of omega t. And how do we find the four constants? The constants from the displacement term comes from the boundary value problem. The constant from the second term comes from the initial condition problem. To be specific, the constant A and B comes by setting the boundary conditions of the spring. We will consider a sample case, a fixed string. Fixed string, which is a string which cannot move by its edges. Okay. A string which cannot move. What does it mean? We do write the boundary problem by its u of 0 is equal to 0 and u of L is equal to 0. This is the boundary condition of a fixed string. If we substitute, if we estimate the u in 0, we have sine of 0 is 0, cosine is 1, so we have a. It is a equals 0. Substituting what remains, so it's just the sine, so the sine of gamma L is equal to 0. This is called characteristic equation. It is called characteristic equation. It is very important. Then you have encountered many times the word characteristic equation, the term, the phrase characteristic equation, when you solve problems. For instance, you saw with the other professors in the first part of the course that if you want to solve the discrete dynamic equations, you will have to set to 0 the determinant of the mass and stiffness matrix, and then the determinant equals to 0 is the characteristic equation. So when we deal with dynamics of continuum media, the characteristic equation comes from the boundary value problem by imposing the boundary conditions. And they are particularly simple in the case of a fixed string. Sine of gamma L is equal to 0. When is equal to 0? When gamma L is equal to n pi. Everyone knows that. So gamma is equal to n pi So the solution of the equation of a fixed string are u of x is equal to sine of n pi over L times x. I will cancel both to go on with this discussion. This is just a perspective because you know the continuum of structural dynamics is a very large subject. It is studied by physicists, by engineers, by so many people that everyone has his own point of view. So we're trying to explain this matter according to my point of view, my information, my background. Perhaps you have yours according to your background knowledge. U of x sine n pi over L times x. So it's so the total solution would be u of x t is equal to the general solution of the second order ordinary differential equation in the time domain is, you know, a cosine of omega t plus b sine of omega t, which is the t multiplied by u of x, which is sine of n pi Lx. We know this term by imposing the initial conditions. How do we set the initial condition? We will not get through this matter, but so we must know the displacement and velocity of each point of the string at the very first time. So when t is equal to 0, u of x when t is equal to 0 must be a sort of u, big U of x. And when u dot of x when t is equal to 0 is a sort of u dot of x. If we impose these conditions, we find A and B. So differently, differently from the boundary conditions, the initial conditions are more complicated because it can be a function. It is we deal with functions, so the coefficient terms will pass through the Fourier analysis. We discussed a little bit last time, but I will not repeat because, well, I want to focus on other things. Okay. So let's go ahead and see that let's forget about time and concentrate on the displacement, on x, on the x solution, on u of x. So the equation is u of x is sine of n pi over L times x. So when n is equal to 1, the shape is like this, because L is the total length of the string. When n is equal to 2, the string is like this, the shape is like this. When n is equal to 3, the shape is like this, and so on. There is an alternance between symmetric and antisymmetric shapes. But these shapes vibrate with a certain velocity, with a certain speed. They go up and down with a certain velocity. And which is this velocity? We know because we said that omega squared is gamma squared c squared. Okay? But omega is a term that we have the sine of omega t, cosine of omega t, which indicates how the term goes up and down, is the natural frequency. We know this term. We are using the same letter just to avoid misunderstandings. Omega square is the circular frequency, which appear in the argument of the sine. So corresponding to each gamma, which this is the gamma, there is always an omega. And omega is this term. Omega is gamma C0. Okay. So omega is n pi over L, is this one, times the square root of t over rho in the case of this string, right? And we add n because it depends on n. So when n is equal to 1, we have this shape which vibrates, which goes up and down according to a certain frequency. This is the circular frequency. And the value of that circular frequency is this one, when n is equal to 1, when n is equal to 2, to 3. So we have this specular to the dynamics of discrete systems, because in discrete systems you studied that there are mode shapes. You know the concept of mode shapes, and each mode shape vibrates according to a specific and well-determined natural frequency. And here we have the same, because we have a shape that we will call it mode shape, which vibrates according to a specific natural frequency. The main difference between the dynamics of discrete and continuum media, and that continuum media have infinite degrees of freedom, because you are not looking for the unknown of the problem is not a vector of displacement. It is a function of x. So x is inside that x, we have infinite dots. So we have infinite degrees of freedom. So we have infinite modes and infinite circular frequencies. This is the great difference between the dynamics of discrete and continuum media. Okay, this is the basic concepts of the continuum. So it must be very clear. That's why I want to repeat it another time. Last time we discussed according to another view. This time we discussed in a different way, but these are the mode shapes, and these are the circular frequency. And we estimated this by using the method of variable separation. Okay, and I wanted to make a little remark on this, and then we will discuss about the propagation of waves. But before that, Let's find and let's solve another for exercise, another boundary value problem. Let us consider a soil. This is the depth of the thickness of the layer of soil. And we know that the wave equation is just the same as u. So it's d squared u over dy squared is equal to 1 over c0 squared d squared u over dt squared. Okay. If we have a soil, we have the earth here. Which are the boundary conditions? So we are looking for the u of x. Here we assume that we have the bedrock. So it is fixed. U of 0, let's start over by this one. From the u of 0 is 0 because we have perfect adherence between the soil layer and the bedrock. And then we have the top of the layer, and we assume that the shear strain is 0. The tau is 0. Tau is g times gamma, which is g times du over dy is equal to 0. So it means that we are saying that g times d big U over dy, big U, that's big U1, and dy is equal to 0. Okay. So the other condition is that du over dy in L is equal to 0. The u in 0, the solution is the same. It's a cosine of gamma x plus gamma y plus b sine of gamma y. In 0, the sine is 0. Then we have a 0, as we had in the fixed string. Then we have the sine remains. If we derive the sine by y, we have the cosine. So we have b omega cosine of gamma L is equal to 0. So cosine of gamma L is equal to 0. This is the characteristic equation. This is different because the solution cosine of gamma L is equal to 0 when gamma L is equal to n pi divided by 2. The cosine is 0 when we have pi and a half. So the solution is gamma is equal to n pi divided by 2L, but gamma is omega divided by c. So it is omega divided by c is equal to n pi over 2L. So omega is n pi divided by 2L times c, but c in C0, right? C0 is G, the shear modulus divided by rho. In geotechnics, it's not called C0, it is called Vs, the velocity of the shear waves. The velocity of the shear waves. You can see it. So omega is n pi divided by 2L times Bs. But omega is 2 pi the natural frequency. We forgot an n. So the f of n is n df divided by 4l. I write it bigger. F of n is equal to n vs divided by 4l. Not L, H. I call it H. H is the depth of the soil layer, right? I don't know if you see the importance of this expression. If you have to build a house, there is always the soil, the bedrock, and the deposit. This is the deposit. We do not build over the bedrock generally. There are many deposits of clay, silt, sand. And that deposit can be viewed in seismic engineering in the optics of the wave equation, where shear waves propagate from the surface to the top. But this soil is like a structure, and the house is another structure. So if there is an earthquake, we can have the amplification if the frequency content of the earthquake is tuned to the natural frequencies of this layer of soil. So we must be careful that the natural frequency of the house built over that soil is not very similar to the natural frequency of the layer of soil. Otherwise, we will have the problem of double resonance. We have the same natural frequency of the house and the soil. So we will have an amplification, a great amplification of the effect of the earthquakes. And this is the simplified expression to calculate the natural frequency of a soil of depth h, by assuming, of course, that the soil has a non-dispersive behavior, that there is only the simplified expression of shear, a flow deformation. I mean, there are immense assumptions. But simplified equations are very useful to understand phenomena, very useful. So many geotechnics do know, do remember that equation, Vs over 4h. Vs over 4h is an expression that you remember like PL squared over 8. The geotechnics know that term as structural engineers know the moment, the bending moment of a simply supported beam. It's a very, very common equation. We can obtain this straight away as we did using the wave equation. Okay, so this is the first part. We reviewed the string, and we obtained the mode shapes and natural frequency of a vibrating string, fixed vibrating string, by solving the boundary value problem. And we introduced the solution of the initial condition problem. Then we solved the boundary value problem in another physical case, the case of a soil of depth h, and we obtained then the expression of the natural frequency. Okay.